Hi, welcome back. Today we're talking about projectile motion. Projectile motion is any object that has started with some velocity and then that's it. After its initial velocity, the object is in free fall. So we're going to go through kind of the nature of projectile motions. We're going to look at the curve and talk about the velocities and the accelerations and where you can find the total height, the total time, and that sort of thing. So let's go. The direction of motion is going to be along the path, right? What it really is if we keep that going, it's actually the line tangent to that point right there. That is your actual velocity. Now, we've already discussed that this velocity has an x component, so v sub x, and it has a y component, v sub y. What we haven't really discussed a whole lot is that this also has an acceleration. So the acceleration due to gravity, in this particular instance, we're going to call down. So our frame of reference is everything down is positive. And so that makes gravity positive. And so this is going to be g equals positive 9.8 meters per second squared. Right? It's always down. And so at this point I also have g, or we could say, let's call it a. At this point up here at the top, we also have gravity, and my velocity, the line tangent, is actually all in the x dimension. And so there's some velocity in the x dimension. Now what we don't see is a velocity in the y dimension because it's zero. There's non-existent y dimension. Everything here at this point is in the x dimension. So my full velocity is also v sub x. My acceleration, however, is still down. If we look at this point right here, the line tangent is going to be my velocity, and then my y velocity, v sub y, and my x velocity, v sub x, are some values. Now, some of the signs that you need to think about, because my reference point is going down, v sub y over here is going to be negative, and v sub y over here is going to be positive. Acceleration is also down, and the whole time acceleration is matching my reference point in this particular situation, so they're all going to be positive. Now what you're going to see, and then we'll talk about the nature of projectile motion, the y dimension velocity here is opposite of the acceleration. And so when we looked at the change in velocity, which is really the acceleration, and the change in velocity was anti-parallel to a vector, it slowed it down. And so as you launch with some speed, then you go higher and higher and higher, this acceleration is going to bite into that y, that velocity in the y dimension, more and more and more, because the velocity in the y dimension is negative. It's opposite of your reference point. So it gets smaller and smaller and smaller and smaller until it eventually comes to zero in the y dimension. But then on the second half of the curve, the y velocity is in line with the acceleration. And so now that the acceleration, or the change in velocity, is parallel with the velocity, they will increase. Okay? And so what you see here is a symmetry, because a was 9.8 meters per second here, and a was 9.8 meters per second squared here. It's going to decrease in speed the same as it's going to increase in speed. And so that gives us a fundamental property of this projectile motion, where I can say that the launch speed is equal to the impact speed. So sometimes they'll refer to this as launch and negative launch, or in this case, because of my reference point, this is going to be the negative launch and the positive launch, right? So the velocity that it starts out with is the exact same velocity that it's going to end with, and the only thing that's changed is our direction or our sign. Now the other thing that we should mention for this is that the v sub x is the same at each position. So all of the x-dimensional components stay the same. So if you ignore air resistance, which you can for relatively small objects and objects that move relatively slowly. So a tennis ball moves relatively slowly, and it kind of sometimes it seems like we just wave away some of the actual physics that's happening, but it really doesn't matter, because any of the air resistance that this ball was experiencing on the way up to help it slow down to zero is also going to be affecting it on the downward side. So it's negatively impacting its velocity on the way up, but it's also negatively impacting it on the way down. And so the change due to air resistance would be canceled out, even if we took it into consideration. And so we don't really need to use it. The other thing is it's just going so slow. You know, you think that, you know, a 90-mile-an-hour fastball, you know, is going relatively fast, but it's not in terms of physics. And so we can neglect some of that air resistance, and so you don't see that displayed in these launches. So there's no air resistance. What goes up must come down, and it goes up the exact same way as it comes down, where A is always pointing down, and the same value. The y's change directions, where v sub y is 0 at the top, and then the v sub x's are all the same as you go through the problem. So let's do an example problem, kind of look at this mathematically. Okay, so what I've done is I've kind of taken out the shape of the projectile motion, and we're going to look at this strictly in a vertical sense. So we're only looking at the y dimension here. Okay, so straight up, straight down. So a 90-degree launch. If I start with an initial velocity of 29.4 meters per second and a initial velocity of, or initial position of 0 when I'm on the ground, what will happen at each point along the way? And you'll notice that my velocity vectors get smaller and smaller, and then they increase at the exact same spot, right? So I'm looking at v sub 1 on this side going up, and then v sub 5 on the way down at this point. The other thing that we need to talk about is the motion map. Okay, each dot represents a time increment of 1 second. Now we're going to use some of the kinematic equations to kind of like show what's going on here. All right, so position. What I usually use for position is the delta x. And so my initial velocity of 29.4, and I've been moving for 1 second, plus 1/2, 9.8 meters per second squared. In this case, it's going to be negative. And so my position at point 1 is going to be 24.5 meters. Velocity, I'm going to do the same thing. I'm going to do, and so when I plug in my numbers, I've got 29.4 plus negative 9.8 times 1 second, and that equals 19.6 meters per second. Okay, sorry, I see a little bit crammed in here. So I'm going to carry that same math to v sub 2, and then I'm going to do the x2, 39.2 meters. All right, take it to the top. This is going to end up being 0, but we can do the math to show you. Change in position, and so on and so forth. I'll go ahead and quick fill these in. We can draw a few conclusions. It doesn't matter how high the object is. The velocities are going to match. The only thing that's changing is your sign. And so we could see at 1 second in, 24.5 meters up. Over here on the way back down, when I come back to 24.5 meters, right, I went past it and then I came back to 24.5 meters, my velocity is the same magnitude as when it was on the way up, only the sign has changed. If you don't trust me, you can do the math yourself and work it out. Same thing for 39.2 meters per second at time 2. The same position on the way down, the height is going to be the same, and the velocities are going to be the same with a change in the sign. Of course, our special point, v at the top, is 0, and the position at the top is going to be max. And so these are some conclusions that we're going to draw. We'll list out the conclusions so it's very clear. Your launch velocity, 29.4 meters per second here, is the same as its impact velocity, negative 29.4 meters per second. The other thing that you'll notice when we start doing the angled launches is that the angle of launch is the same as the angle of impact. So we launched from 90 degrees and we ended at 90 degrees. Okay? If we launched at 45, we would land at 45. So let's go ahead and list out all of the kind of the takeaways in projectile motion. You might see this word postulates pop up here and there. These are going to be the projectile motion rules. People have experimentally figured these out, mathematically proven these, and so they're kind of the same all the time. The first one, path is symmetrical. T up is equal to T down. So the time it took to get to the top is the time it took to get to the bottom. V at H max was equal to 0 meters per second. 3, A is always equal to 9.8 meters per second squared. It could be up or down, and so that will affect the sign. X is always positive. V can be positive on the way up and negative on the way down, or vice versa depending on your reference point. V launch is equal to negative V launch. So the launch velocity is equal to the impact velocity, and that goes the same for the launch angle. I think I got them all. Okay, so we call it alphabet soup because it's a little bit crazy looking, right? So let's take it down, take you through this. The distance in the x dimension, I'm going to look at the point at the end. So keep in mind that a projectile motion kind of looks like this. And so for distance, I'm looking at this point right here. So you have the total amount of airtime, the velocity in the x dimension pulled from the launch of the x, so taking into consideration the angle that it's launching at, the x only vector of that launch speed is going to be used, and then it will spit out this delta x in distance. Okay, so that'll be the total distance. If you're looking at height, you want to know how high something went. Well, that's all going to be in the y dimension, and I'm going to look at this point right here at the top. And so my delta x in the y, my change in position in the y, is going to be h max, this case, total height. That's usually what it's going to spit out here, delta x, or the delta y, or the delta x in the y, or h max. There's a lot of different ways to write this. And I need the y component of the launch speed. So again, taking into consideration the angle and the velocity vector that I'm launching at, I'll have to do some trig to find its y component of the initial launch speed. Okay, and that'll go in. And then v at the top, this is actually v top y dimension only, because the vx at the top is the same as the vx at the launch, right? So the v top in the y dimension is 0 because it's changed direction. A, negative 9.8 meters per second, and that will kind of keep things consistently. But you can switch this. It's not set in stone. If you do switch this, this is going to be your negative launch speed, right? And then T at the top is T up, or half of the total airtime. We can divide this. The area that this thing is covering is the same here as it is here, and so the time increment T equals T, right, along the bottom. So So that is half of the total time. The formula that we usually do is this displacement is equal to the initial velocity plus 1/2 h squared. So that comes from your kinematic equations. So if I want to find the time, I'm going to look at the displacement in the y dimension and make that 0 because I'm on the ground. I'm over here at the ground level. And I want the launch speed and the negative launch speed for the y dimension. So the speed of up, the speed of down, the a is going to be negative 9.8 meters per second, and my total time, and the formula that we usually use is a variation of that. A equals the change in velocity over the change in time. We change it to fit our purposes. Okay, there you go. That's projectile motion in a nutshell. We'll do a lot of practice. Good luck.